Thanks so much for this kind invitation. It's really very nice initiative by Enrico and Alessio. So thanks for doing this. And yeah, so the key point of my talk is that there is connections to ADS-CFT. So I'm really a high energy physicist. But on the other hand, there will also be lots of connections to condensed matter physics. And I think one of the nice thing of this topic is that we combine aspects of high energy and condensed matter physics. And I should mention that I'm a member of this program called CTQMAT, which is a so-called cluster of excellence. So this is something in German science landscape. So it's funded by the German federal government, and which is really an initiative by condensed matter physicists. But I'm also a member of this team. It just got renewed for another 7 years. And so that offers a lot of possibilities for exchange with condensed matter physicists and myself, so being in ADS-CFT. And you will see the examples of this in the talk. So the background is the castle here. I mean, we have two castles in Würzburg. It's a very nice university town. And if you have ever the chance to visit, let me know. All right. So as a further motivation, let me say that how did I come to this topic? Well, this is in the context of a program which I call discrete holography. And so what is this? So the goal is to establish a holographic duality in the sense of generalizations of the ADS-CFT correspondence on a hyperbolic tiling. So hyperbolic tiling, you can see an example here on this picture. So it's a projection of a two-dimensional hyperbolic space. And so all these polygons there, in principle, they are all of the same size, but due to the projection of this negatively curved space, they look closer to each other at the boundary than in the interior. And also it's a non-compact space, so essentially there's an infinite amount of these polygons until you reach the boundary. Now, the original ADS-CFT correspondence, due to Maldacena from 1997, establishes a duality between two theories. And so now I'm going to use a much more broad definition of this word duality, in the sense that what we are after is really a link or a map between one theory as given by an action if you're a high energy physicist, or a Hamiltonian if you're a condensed matter physicist, and another theory given by another action and another Hamiltonian. And assume that you have two such theories and they describe a physical system, they describe the same physical system. So if they describe the same physical system, then obviously they must be related to each other. And this relation I'm going to call a duality. Of course, there's also a mathematical term, duality, and actually that plays a role as well. But let's stick to this physical definition for now. And so now the idea is, can we go beyond ADS-CFT, which is based on string theory and branes, and definitely on differentiable manifolds, so Minkowski signature spaces. And can we establish this duality more generally, which would be a much more general application of the so-called holographic principle, according to which the entropy scales with the area rather than the volume, as it does for black holes, for instance. And so the motivation I have is, can we extend the holographic dualities beyond the original ADS-CFT case? And one example being, can we write down one theory in the interior and one theory on the bulk of the space, such that they describe the same physics? So that's one question. And the other question is more motivated by my colleagues here working in condensed matter physics, who are many of them are doing topological insulators. And there's this idea of these so-called topologic circuits. So where they just build analog systems of condensed matter systems by using electric circuits. And they also build kind of crystals of this hyperbolic type. And they really exist in the lab. And so and that's another motivation for looking at these dualities that I'm going to talk about. So by the way, if you have any questions, just please interrupt me right away. I mean, it's a topic bringing together various different aspects of theoretical physics. And so if you have any questions, just please ask. Oops, no, okay. All right, I have lots of material and I'm sure I'm not going to go through everything, but let me just give you an overview also as some further motivation. And if I don't manage to get to the end, maybe you're interested in looking some of these things by yourself later. So I'm in the middle of explaining the motivation for what we are doing, and then next I'm going to explain how to generate these hyperbolic tilings, which is of course at the basis of of this work. And then I'll discuss a few of the predictions for these electric circuits that I mentioned, which are kind of cute because you can model things that are known from supergravity string theory really in the lab, essentially. I mean, so far we have only theoretical work, but in principle, you could actually build these circuits. And then so the main topic of my talk today is the paper that you chose, which is the one about this antiferromagnetic Ising model on hyperbolic space. But leading up to this, I mean, this is a kind of follow-up paper to a paper that we had previously, which is about discretized so-called Jacquard-Teitelbaum gravity. And there, what we do is we actually map a particular gravity action to a particular Ising model. I show you how and which one. And that was more from a kind of high energy ADS-CFT perspective. But then this led us with our colleagues from this excellence cluster to also look at the antiferromagnetic case. So this work is more from the condensed matter side. Okay, and then I probably won't have time, but let me mention that there's related work. I mean, so these points 4 and 5, they're more about the bulk, so what's happening inside the space. But then if we really want a duality, we also have to explain what happens at the boundary. And these two papers, they're actually more about what's happening at the boundary. And so actually we constructed some spin chain model which reflects the symmetries of this bulk tiling and studied it using particular RG techniques and tensor network. And also we calculated the entanglement entropy. And then we also say that another very topical question in ADS-CFT is the use of von Neumann algebras to describe holographic dualities. And there we have some nice work where we applied this to a toy model, which is a Majorana fermion chain. And so that's also in this context of holography, and this fermion chain is also something more to be thought of at the boundary. But as you already see, if I go back to my central program here of establishing this duality, so we have various pieces of the puzzle, but we have not yet reached that we can put everything together and say, okay, here we are our two Hamiltonians and they are dual to each other. But nevertheless, this generated already quite a lot of very nice work. And we hope to, in the future, to put this all together into a coherent picture. Okay. Here's a lot of papers that may be relevant, but let me just very quickly, I mean, later I won't mention them anymore, but so this is what this talk is essentially based on. But let me just tell you a little bit about the history and the context of the work that you chose for the talk today. Okay, so this is a paper where we implemented the so-called Breitenlunder-Friedman bound, which is something that I'm going to show to you on the next slide, essentially, or in 2 slides, in this discrete system. So that was done by our group here in Würzburg. And the second paper is a paper where we teamed up with our colleagues in condensed matter physics, Ronny Tomane and Igor Böttcher mostly, and Martin Greiter, some others, where we actually use these hyperbolic lattices to simulate them, at least theoretically, in an electric circuit. So let me show you quickly these nice results. And then this is a paper in collaboration with Matthias Wolter, who is in Dresden. So I should mention that this cluster of excellence is based in both Würzburg and Dresden. And so we collaborate with people in Dresden. And so this together with Matthias Wolter, who is a famous condensed matter physicist, we started to map gravity actions to Ising models in hyperbolic space. And then the paper that is the main focus is this one, together with Roderich Messner, Matthias Wolter in Dresden, and their student, I think this is Matthias' student, Fabian Köhler, which looks at a slightly the same type of Ising model, but a slightly different perspective because there will be anti-ferromagnets, which is this recent paper here. But okay, as I said, it's in some sense it's a follow-up to that paper. Okay, and then maybe at the end I will have some brief time to mention these papers which are more about the boundary of this hyperbolic tiling space. And so they were done with my student Pablo Bastero and Giuseppe Lugirio, who is now he was a postdoc here, but now he's in Stockholm. And Jonathan is also my student, René is my collaborator, and Joey was also a postdoc here, and he's now in Berlin. And then finally, this is the paper about realizing von Neumann algebras inspired by ADS-CFT in these interacting Majorana chains. Okay, so some advertising. I hope you may be interested in looking at these. And sorry. Okay, so now let me get slightly more technical. So we want to establish ADS-CFT on these hyperbolic tilings, and so let me say a little bit how you actually construct them. So these are non-compact spaces. In principle, you will have an infinite amount of these polygons. So if we come from a high energy perspective, we consider Lorentzian ADS 3, so in 2 + 1 dimensions, 2 space and 1 time dimension, and we fix a constant time slice. And so that's shown in this plot here. So an anti-de Sitter space is really like a cylinder with this negative curvature. And then if we fix a constant time slice, we get this blue disk here. And then, so you can define some geodesic distance on this disk. And then, so this is all continuum space now. How can we actually find a tiling inside this blue disk? And so there are actually many more tilings of hyperbolic space than of flat space. Because if you look at one of these examples, and you denote by P the number of corners in each of these tilings. So this is a heptagon, so this would P would be 7. And then you look at how many of them meet at every corner. So that would give you the number Q. Okay, so Q is how many of the polygons meet at the vertex. And then you can actually show that you have a hyperbolic space. So anti-de Sitter is also an example of a hyperbolic space if this inequality is satisfied. If you have an equality here, then you get a flat space, and if the sign is in the other direction, then you would get a positively curved space. And so here are some examples. And so by a conformal mapping, so these are the geodesics in this space. By a conformal mapping, you can map it to these more regular looking tilings. And so this is a 5-4 example because we have pentagons and 4 of them meet at each corner, and this is a heptagons and 3 of them meet at each corner, and here we have hexagons and 4 of them meet at each corner. And then you can, in this plot, define some geometric quantities, how to describe exactly what your tiles look like. Okay, so these numbers P and Q, they're really important in the subsequence. So this is the number of corners and the number of polygons meeting at each vertex. Okay, so as I said, anti-de Sitter space or negatively curved spaces are non-compact, so in principle they're infinitely large. And so one further important construction rule, which is following this paper that I mentioned here at the top right corner, is to construct these tilings through something which is called an inflation rule. And so what is this inflation rule? Well, there you construct layers of these tiles concentrically. So you start with some tile in the middle. So in this case, it's a hexagon. Here, it's just a square. And so that will be your zeros layer. And then you construct concentric layers of these tiles. And then, so one thing, if you want to do numerical simulations later on, there's always this problem that we cannot do this for an infinite amount of times, but so we have to stop after n layers, which then would be the boundary of this tiling. And one thing that we will see for these Ising models is that the structure of these boundaries, they will have a big influence on how exactly the physics of the ground state, for instance, is going to be. Now, what's also important is that we have two types of vertices, the red and the blue ones. And so the difference is that the red ones have in the same layer or in an inner one, they have two neighbors. So this has two neighbors, for instance, and this point here also has two neighbors, while the blue ones, they have three neighbors, one in the interior one and two on the same level. And so the way you construct these concentric circles or sequences is that you replace every vertex by a sequence. So if A is the red one and B is the blue one, then from going from one layer to the next, these concentric layers, they're obtained by replacing this letter by this word in such a way. So this is for the 6-4 tiling, and this is for the 4-5 tiling. So then, in effect, what you then find that the boundary of the tiling after a large number of these inflation steps is characterized by a long aperiodic sequence of red and blue dots of A's and B's. Okay, and we use this construction principle for most of our applications. Okay, so as I said, we would like to take a new step toward a discrete duality. So here's the standard ADS-CFT correspondence in this low dimension. So on one hand side, we have a quantum gravity theory in ADS 2+1, which is conjectured to be dynamically dual to a two-dimensional conformal field theory on the boundary. And now here there's a big question mark, and I mean, this question mark is not going to be resolved in this talk, although I showed you lots of very nice results, but still still remains an open question, sorry, that we would like to address. So if we have a theory on a discrete geometry of this PQ tiling, in what sense will this be dynamically dual to a quantum chain at the boundary of this tiling? And so I show you example for these in those theories, but what we haven't managed yet is to get this map working perfectly. But that's the motivation, or at least one of the motivations. All right, now let me go to the other motivation that I mentioned at the beginning, that so we would like to model these hyperbolic tilings using electric circuits. And so in particular, what we managed to do is to take some predictions from gravity theory, and which are from continuous spaces, and implement them in this discrete setting. And let me show these to you. Okay, so the first one is the so-called Breiten-Nona-Friedman bound. So this is a result from supergravity from some time ago now, by two famous scientists working in supergravity. And so what they actually found is that if you look at fluctuation modes on a continuous hyperbolic space, then there's an enhanced region of stability as compared to flat space. So, as you probably know, so if we have a potential which depends on some field, then obviously if it's curved upwards, so the mass is positive in flat space, then you have a stable potential, whereas if the mass squared is negative, then you get an unstable situation. So if there's a small fluctuation, then your field vacuum excitation is going to run away from this point. And if you are in flat space, going from here to there, it just means you flip the sign of the m squared term in your action of this term. Now, if we look at the two-dimensional, I mean, so these two authors, they found this bound now in general dimensions. Here, I'm just focusing on the two-dimensional example. So if our hyperbolic space is written in coordinates theta and phi, like this, so that's what we're going to use in the subsequent slides. Then in general, what happens if we have an action for a scalar field, then in this hyperbolic space, there's also a square root g here appearing here in the front. And so actually there will be a 0-point energy term which comes from the curvature and modifies this phi squared term here. And then according to this bound, so L will be the so-called anti-de Sitter radius, which is a constant here. And m squared now, so you will still have a stable situations, a potential of this type, if m squared is slightly negative, so if it's bigger than minus a quarter. So this number depends on the number of dimensions, but here in this low dimensional case, it's minus a quarter. So if m squared times the scale is larger than minus a quarter, then you still are in a stable situation. And now what we did was to realize this in this context of these discrete settings. And that's shown on the slide here. So let me just say again, so this supergravity result, of course, is for continuum spaces. And so what we did in this paper is to show how it's realized in this discrete case. So we look at tilings of this type. And so the different colors here are for different values of P and Q. And so now, so here, this equation, this actually leads to the Klein-Gordon equation. And if we discretize it, it will take a form here like this with some weight factor here. And again, so the issue is that we have to also introduce a cutoff of at the boundary, because just for practical reasons, we cannot simulate on an infinite dimensional lattice. And so the cutoff here at the boundary will play an important role. Okay, so here what we see is exactly the m squared term here with the scale, the ADS radius, to make this a dimensionless quantity. And the dotted line is the value of this bound in continuum space where it's at minus a quarter. And now what we plot here is the value of the field in the center of the space, so one of these vertices of the central tile. And we see that it diverges at discrete points if we impose a cutoff, a finite cutoff. And so these results, they even still hold in the continuum case. So you see that if we have a finite cutoff, then we get isolated singularities. Now, if we decrease the size of this cutoff, then they become more dense, and they also approach this bound, as you can see. So, and that's exactly shown here on the right-hand side. So, oops, I'm sorry. Here, what you see is the value of this cutoff. And so this is this Umklamm void, or this, which is another name for the singularity that we see here. And so now if we send epsilon, the cutoff, towards 0, then the black line in the black squares is what you have in the continuum. This you can actually calculate analytically, and we confirmed it also with some numerics here. And then you see that, interestingly, for any value of the tiles, so we know how many corners they have, how many meet, there seems to be some universal behavior approaching this bound. So the inset now is actually done for these electric circuits. I mean, here this is just numerics, just with this discretized Klein-Gordon equation. And so that's still an open question. Is it really universal? And why should it have such a boundary? I mean, there's a mathematical reason that you can actually show that the boundary of these hyperbolic tiles still approaches a circle. Whereas if you do it in higher dimensions, you will actually get some fractal structure, but not in 2 dimensions. It will just be a circle. And given that the boundary looks the same for all of these tilings, maybe that's an indication that they should all approach the same value. But it's interesting they do it all in a very, very similar fashion. And so that's a very interesting phenomenon. And I mean, that brings us to one open mathematical question, because here we are talking about discrete infinite groups, and so it would be nice to know their representations, but some mathematicians, they have many results on Lie groups, and they have many results on finite discrete groups, but finite infinite groups, I mean, there are still many questions which at least maybe they're known to mathematicians, but they're not formulated in such a way that they're easily accessible to physicists like me. Okay, so That would be nice to understand further here the group theory structure of this. But anyway, it's a very interesting observation. And that actually reflects, if we now go to these circuits, so we can actually build now a circuit. I mean, okay, this is an idealized a circle where there's no resistance, but okay, just to show the idea. So there are inductances and capacitances, and if they're arranged in such a way, then you can map this discrete Klein-Gordon equation to using the Kirchhoff rules and just standard relation between the voltage and the current and the resistance and the inductance. Sorry, you can relate this, and then you can actually now, if you make an ansatz of this form where t is now just a time which passes in the lamp, and you just make a plane wave ansatz, and then you find this relation between this term which determines the stability and the frequency, the inductance and the capacitance, and these weight factors from the Klein-Gordon equation. And so if you hit one of these singularities that I showed here, then in this idealized case, if you just incited at the beginning, even if you stop the drive at some point, you create a wave that goes on forever. And if you're away from one of these singular points, if you stop the driving, then also the mode is going to decay, the response is going to decay again. So it's very interesting that these quantum gravity things can be modeled in these electric circuits that serve as a model for. I mean, mostly this idea was used to study topological insulators, but we can also study these putative materials that have this hyperbolic structure. Okay, so the next paper also with colleagues in condensed matter physics is that now we can also measure 3-point functions on these hyperbolic lattices. Again, this is just a theoretical study, but in principle, you could realize this in the lab in an electric circuit. And so what we have here is a proof of principle for realizing this. And now we look at 3-point functions. So in supergravity, you draw something called a Witten diagram. So this is the boundary of your hyperbolic space again. This is the interior. And then you can actually calculate using propagators that, or propagators in hyperbolic space, and you just have to integrate over this point. So there's some Feynman rules there. And then if you integrate over all these points, you just get a result for a conformal 3-point function at the boundary of your space. And of course, because in ADS-CFT we have conformal symmetry, the 3-point function is determined by the symmetry, and this is actually reproduced by the bulk computation, which is in the continuum case is done by these propagators in curved space. And now in the discretized theory, we can use a so-called adjacency matrix formalism to reproduce this. So that looks like this. So we can introduce a hopping term to model the kinetic term, and then we still have vertices then of this type. So now if we want 3-point functions, we also need a cubic vertex. And then we use the 2-point function to determine the scale dimension, and that we use to fit the 3-point function, and it actually fits very well in these examples. So in ADS-CFT, there are some fundamental rules that tell you that the relation between the mass of the fluctuations, again, L is just the anti-zeta radius that sets the scale, is given by the dimension of the operators at the boundary, and D is just this dimension of the boundary theory. And then by a so-called LT-SPICE simulation, which is a method from semiconductor physics where you can simulate the propagation of voltage and current through some circuit. We apply this to calculate these correlation functions, and we find a very nice match between the continuum results, between a lattice computation and the circuit computation. So that's shown in these diagrams here. And in the continuum case, if we look at this type of interaction here, the mass will be such that this dimension is 1, but there will be some lattice effects which give us 1.18, I think, in these plots. So that's written here. And but nevertheless, so this is in the case when there's a black hole in the middle. Actually, this is just anti-de space without finite temperature. So we see that so the orange is the continuum calculation, and then the different dots are the lattice in the circuit computation. So the singularity comes from when two of the points are actually coincident, as expected for the correlation function. And we see a beautiful match between all of these, which is quite nice. Okay, so this is a proof of principle that you could realize these gravity predictions in a circuit that you can build. All right, after this very long introduction, now let me come to Ising models. I don't know, maybe I should pause. Is there any question at this stage? Mhm. Mhm. Uh, okay, I see what you mean. Well, okay, so what we did is to actually, so we start with this theory, okay, and then we just discretize it by taking this discrete version of the Klein-Gordon equation. So in some sense, we start with the same theory, but we discretize it. Okay, and this dotted line here is the continuum result. Okay, and so that this is the continuum result when the cutoff goes to 0. And so this line is the continuum result with finite cutoff, and you can see it approaches this line. And these color dots are now for the different tilings. So in some sense, this is all, I mean, at the level of precision that I'm doing here, it's this theory in the bulk. But nevertheless, I mean, it's still interesting that whatever tiling you do, all these points seem to follow exactly this continuum version. So the colored dots come from the tiling, and the parameter here is the cutoff at the boundary. So yeah, yeah, I think it would be very interesting if there were a way to prove that it has to be like this. And but again, as I said, this would mean that we understand more the mathematics of the representations in this discrete. So that's the idea. Yeah, thanks for asking. Thank you. Thanks. Okay, thanks. So now let me move on to the Ising model. Um, So one very prototypical model used by many people in holography to go beyond, say, the standard ADS-CFT paradigm, where you have a kind of semi-classical limit of planar diagrams and n goes, so the rank of the gauge group going to infinity, and is to look at this JT, Jakob Teitelbaum gravity. So this is in 1 + 1 dimensions, or you can also go to Euclidean version, which is in 2 dimensions then. And so that is a kind of toy model of ADS-CFT, which has lots of very nice features, and many calculations can be done explicitly. So that's a nice starting point to actually discretize this gravity. And as I will show to you, then this discretization gives you an Ising model. Okay, so that was done in this precursor paper to the one that you found in June this year. So this is a paper from last year. Okay, so again, this is our group from ADS-CFT with my colleague Matthias Wolter, who is a condensed matter physicist. Okay, so this Jakob Teitelbaum gravity in 2 dimensions is given by this action. So first there's some topological term, and then you just have an Einstein-Hilbert term with a scalar coupling here. And then there's a cosmological constant, and because this constant is cosmological constant must be negative because we are talking about hyperbolic spaces. You get a plus sign here. Actually, there's 2 minus signs canceling, and then there's a boundary term here. So with the boundary curvature, and phi is a dilaton, if you want. So there's a scalar coupling here. And so this has been, as I said, the continuum version shows many, many beautiful features, which took us quite a way beyond the original ADS-CFT correspondence, and some version of the so-called SYK model, so the Sachdev-Kitaev model, is actually dual. So this is a double-scaled version of this model, is dual to this gravity action. What I'm following here is also some continuum results of these authors here. And what they actually managed to do is to map this gravity action in the continuum case to a matrix model at the boundary. And so now one idea that we have is to do the same thing for the discretized case. We are not all the way there, but we made some progress, and this is what I'm going to show to you. And there's an L missing here, it should be Ising model, okay. So the idea is now that, well, we discretize our space with one of these tilings, and essentially what the spins are going to be, so there will be red and blue, which means spin up and spin down. So it's actually a spin a half Ising model. And the point is that the partition function of this Ising model will be related to the resolvent of this gravity theory. Okay, so that's again borrowing some of these continuum results. So red just means there is space, and blue, and spin up, and blue means there's no space and spin down. And again, we cannot go all the way to the boundary. We have to stop at some finite amount, and that again will have a lot of boundary effects. Now, so the dual lattice of this can be mapped to an Ising model. So I'm going to show this to you in a moment, again, where red means spin up and blue means spin down. And but it will be a very strange Ising model because the gravity actually demands that you can only have two domains. Okay, so normally if you have an Ising model, then you have lots of different domains, but actually the length of this curve here actually is a parameter in the gravity theory. And so this means that you can have only one domain between space being there and not being there, so between spin up and spin down. So, and that, of course, very much constrains this Ising model. So, and okay, maybe let me explain a few more details about this. Okay, so first of all, okay, so we're going to discretize this theory. So we see there's a curvature term here, there's a cosmological constant, a boundary term, and a topological term. And so now the smooth manifold is replaced by this simplicial complex made out of these tiles. And the curvature just then becomes a deficit angle at the vertices. And now if we do this for triangles, so we said P equal to 3, then this is the value of this deficit angle. Okay, so it depends on the different angles of the triangles, and so they don't add up to pi then now anymore. And so if you do that, then you can calculate the curvature, and for every vertex you get such a contribution. And there's also this intrinsic curvature at the boundary, which you treat in a similar way. Okay, so now we borrow on some results from the continuum case, for instance, by these authors, and where there's also other papers by Iliescu, Verlinde, and some others. So who actually showed that the path integral for this JT gravity on the disk is obtained from a sum over closed paths, which is weighted by the area enclosed. Okay, so this would be this path gamma. And so in this limit, where we are in the semi-classical approach, you can actually map your path integral to something which is just dominated by the length of this curve. Now, if we take this ansatz and go to an Ising model, then the sum over these closed paths becomes actually a sum over spin configurations, where just inside this loop we have spin up and outside we have spin down. Okay. And so what we then find is that the resolvent of this gravity model corresponds to the free energy of the Ising model. So that's a very interesting connection. And that has appeared, I mean, there's some papers already from about 10 years ago where people studying tensor networks and, for instance, random tensor networks, they also showed that, for instance, the second Rayleigh entropy becomes also the free energy of an Ising model. There's some papers by Patrick Hayden and collaborators, for instance, on this. So in that sense, it's not so surprising that this happens here as well. And so we will always work at relatively low temperatures because the low temperatures correspond to the semi-classical planar large N limit of the ADS-CFT correspondence. All right. So now if we start with our JT action and we insert these discrete values for the curvature, then after some calculation, we arrive at an Ising model. So there, again, there's a topological term with some Euler character here. There's one term with a magnetic field. So it's a nearest neighbor interaction model. So beta is the inverse temperature. And here is the coupling of the nearest neighbors. And so the various parameters reflect the gravity parameters of the original gravity action. So we have the boundary and the horizon value of this dilaton, and now the magnetic field and the coupling essentially reflect the geometry. And since we set p to 3, so we only work with the triangles, then q just counts the number of triangles meeting at each vertex. Okay, and now we can simulate our Ising model on this hyperbolic space with these parameters. So we just use a Monte Carlo approach. And so the result is shown in this plot, and let me try to explain what is shown here. So actually, because there's a constraint from the length of this boundary, there will be an effective coupling where this J coupling here is shifted by the ground state energy. So that's why we can scale this. And here we plot the free energy. Now, as you can see, there's one antiferromagnetic regime or small positive values here of this coupling, and then here it goes to larger values of the coupling. Now, in this regime here, now we're in a region which is dominated by this magnetic field, and that means that the free energy is linear in this effective coupling. And on the other hand, here, this is a region where the J becomes very large, and that's the coupling-dominated regime, and then the free energy is constant. And okay, so these two things, they can be calculated analytically, but the gravity will be, so maybe the limiting cases in terms of the Ising model because of this strange boundary condition is here in the, so one boundary condition that we impose here is that we make all the spins pointing in the same direction at the outermost ring of tiles. And then if the magnetic field is very large in the other direction, then the spins try to align with this magnetic field, and then we get this one huge domain of things pointing in this direction. On the other hand, in this here, where the magnetic field doesn't play any role, then the system prefers that all the spins point the same way as here at the boundary, which we set as our boundary condition. Okay, so this is when the coupling is positive and we're in this ferromagnetic case. And so now, but the region that's interesting for gravity is really the one in the middle. But we can simulate this Ising model. The only problem, we have a slight numeric issue there, which is due to the conformal symmetry of the problem. Even if you make the system bigger, it doesn't really help you to simplify the calculation. And so that creates this little hump, which means that we don't hit the ground state here. This curve should interpolate in a smooth way between the two regimes. But that's
Okay.
yeah.
Can I ask you about this? So do you think the correct free energy should be monotonic then?
Yes, definitely. Yeah, it should.
Okay.
Yeah, I mean this is a numerical artifact because we don't. I mean we look at this the system settling down and here it just doesn't find the ground state. It goes.
Is there some monotonicity theorem for this free energy?
Yes, I mean, okay, at least at the level of physics, you can argue that it must be smooth. I mean, because everything just depends on this constraint of the size of the domain, and so there's no reason why there should be a hump. Okay, so and we can explain where this comes from. It's just in this region you have conformal symmetry, so and which is reflected in the a hyperbolic space has also conformal symmetry and. If you make the space bigger, the problem doesn't become simpler. So I mean, if you really, you can, even if you go with a very big computer, it will take forever. But certainly, of course, I mean, if you really do a big crunch with lots of numerical power, you should be able to. Or if you find an ingenious way to avoid this scaling with the system size, I mean, that would also be helpful. And then we should see this.
Okay, thank you.
Behavior. But that's an interesting numerical problem, actually. Yeah, thanks for asking. All right. So as we can see here, here in this model, this model came from starting with gravity, and then we discretize, and we have a magnetic field, and we have a coupling, and we have one regime which is antiferromagnetic, and one regime which is ferromagnetic. So that's where we were. And now here in this paper with the condensed matter colleagues, we come from the other side. Okay, so this is the paper which you asked me to talk about, so I'm getting there now. So now we come from the other side and we say, okay, we don't know about gravity. Let's just look at an Ising model in hyperbolic space, but now with an antiferromagnetic coupling. So in this case, however, we don't switch on the magnetic field, at least yet. And due to this antiferromagnetism, we will have frustrated spins, and that will lead to this spin liquid behavior. So let me show this. Oops, sorry. Okay, so now, so we just start with an antiferromagnetic model here. In the sense, again, it's nearest neighbors, just spin and a half particles. And we take the coupling constant to be negative, which means it's an antiferromagnet. And then again, we take triangles, but now on this hyperbolic space. But even if you just take triangles on flat space, you know that there is this issue of frustration in the sense that if one spin points up here and the other one points down there, then the spin that is here doesn't know what to do because it wants to anti-align with this one and with this one, and that's not possible. So there's two equivalent states which are still somewhat excited because you really would like to anti-align with both of them, but that's not possible. Okay, and so this means there are two equivalent states here where the spin at this question mark point can actually point either up or down. And this frustration leads to a ground state degeneracy. And that already happens in flat space. Here it also happens, but in the end, this degeneracy will be slightly smaller than in the flat space case, but still it has a lot of effects. Okay, so now our very good student, he did a Monte Carlo simulation of this. And okay, I already mentioned a couple of times that we have this non-compact space, and so it's very boundary condition sensitive because I mean you just cannot do an infinite lattice, so you have to cut off somewhere. And how do you do this? So in any case, what we do is to use open boundary conditions, which means that energy can flow in and out at the boundaries. Okay, and that's a kind of way of simulating that. In principle, the lattice should be infinitely large. Okay, so now what happens? So okay, so here's some plots of what happens with this antiferromagnet on this hyperbolic lattice. And okay, so I remember at the very beginning of the talk, I explained that we use these inflation rules to construct the tiling. And so that's exactly what's done here. So we get a lattice where we build these concentric circle layers of tiles. And that gives you a particular structure of vertices here at the boundaries, which is the one shown here. And then you actually, so the blue, so white and black are now spin up and spin down. Okay, so here we use these open boundary conditions. So we cut off after a finite number of steps, and so that's where the boundary conditions are imposed. And then you see that so the blue lines corresponds to anti-alignment, so there's no frustration there, and the red lines connect to vertices with the same color, so that corresponds to the frustration. And so then you already see, because there's always equivalent um, configurations that lead to the same free energy, which includes this frustration, then we actually end up with a finite entropy in the lowest energy state of this model. Okay, so here you see the blue ones are the ones where there's anti-alignment, and the red ones are the frustrated ones. Okay, so here this is the correlations, and I will talk about them in a second. Okay, so as I try to argue, because you have different configurations at lowest energy, this actually leads to a finite entropy even at 0 temperature, and so we actually calculate the entropy and as a function of temperature, and so this is for the different lattice sites, and so we see that it actually goes to a constant here. So my condensed matter colleagues, they also had a dual approach using dimers, and so this means at strictly 0 temperature, they can also analytically or semi-analytically compute this value. And it's definitely finite. Okay, so that's clearly a consequence of this frustration. So then this is the heat capacity, and so it's quite similar. It's not very sensitive to the lattice size, but as you can see, it is smooth. I mean, there's no phase transition there. I mean, a phase transition would mean that there's a spike here for a second order phase transition, but it is just smooth. So we don't have a phase transition. I mean, it's just looking at this Monte Carlo simulation. And sorry. So other things we calculated is the energy per site, and as you can see, it essentially goes to minus J times N. And again, you can actually calculate this analytically using this dimer, dual dimers. And so the energy gap in this case, because it's an antiferromagnet, is 2J, and then you can actually show that the difference between the energy of the lowest state at some temperature minus the 0 temperature one is given by this expression here. Okay, then we also looked at the correlations which are here, and so now here there's two different types of correlations. So here this is the coupling, and so this is the correlation function. And here L1, L2, L3, and L4, the boundary, correspond to these different concentric layers. Okay, so L1 would be here, I mean, and then L2, the second circle, and then L4, the boundary. And at the boundary, you can see there's no frustration here. In this type of boundary condition, which we get from this inflation rule, there's no frustration at the boundary. So everything is perfectly antiferromagnetic if you just walk along the boundary. Okay. And since there's no frustration here, then actually the correlation will be less strong as in these frustrated cases. And so what is interesting, so here, because of this absence of frustration, the correlation goes to 0 here. So this is the correlations inside these layers, okay? And that's the correlation between the layers. That's shown in this plot here. And then you see it's a slightly non-monotonic behavior, because here the innermost stays here, and there's a crossing between the second layer and the first layer. Okay, so which again means in the very middle, there's less frustration than in this intermediate region. Okay, and a similar structure reflects also if you look at correlation, say, between layer 1 and layer 2 and layer 3, and layer 3 and layer 4, which is at the boundary. Okay. So you see that there's a relation between the degree of frustration and the correlation that appears. Okay, so comments. So as I mentioned, the ground state of the ferromagnetic Ising model on a planar graph can be mapped to this dimer covering problem, and with this help, my colleagues actually semi-analytically computed the ground state entropy, which is finite. However, it's slightly larger than I mean, in absolute. So it's there's less frustration than in the flat space case, okay, but still it's there. And so the system has now the properties of a classical spin liquid, by which we mean the following. So as I showed using the heat capacity, there is no phase transition at finite temperatures, so that's a characteristic of a spin liquid. There's no long range order at 0 temperature, and then there's this existence of this finite residual entropy density. Now, okay, that's interesting from the point of view of having a spin liquid, but now if we aim for a holographic dual, let me mention that also if you have a Reissner-Nordström solution of supergravity, which is for a charged black hole, then it will this geometry also has an ADS2 subregion even if you're in higher dimensions, and this will also always have a residual entropy density. I think last week Subir Sachev gave a talk, and he wrote a very nice paper already back in 2015 when he promoted this use of the SYK model in ADS-CFT, and so the SYK model has a precursor, which is the SY model, which has Weil fermions rather than Majorana fermions. And so for this Weil fermion model, you can also show very nicely how there's a relation between the charge of these fermions and the entropy density, and that is actually very similar for this charged black hole, this Reissner-Nordström, and for this such a Phi model. And okay, so that just points into, so if I come back to my goal of actually finding a dual between the boundary theory and the bulk, the fact that these antiferromagnets have this finite residual entropy density, this is of course very interesting, and that might lead into a direction of finding this gravity dual. Of course, here in this case, now we use these open boundary conditions I showed you before, and when we came from the gravity side, that this domain wall played a very important role. But here, of course, because we start from condensed matter physics, we don't know about this. And so, if we want now to go the other way and construct a gravity theory from this model, we have to think what to do. But I mean, given this finite entropy density at 0 temperature, that really gives a clear sign that there should be a gravity dual there. And so that's something to explore further. Okay, I'm looking at the time. Oh yeah, the time is already up, so I should probably stop. All right, let me quickly say what other things I have. Yeah, I mean, the last thing I want to emphasize is, the boundary are the whole situation is very sensitive to the boundary. So if we now just by hand add these red extra points that you can see here, then we actually get a ferrimagnetic ground state. So by which we mean that the different layers change between spins pointing up and down. Okay, so there will be much more order than in this case. So it's very sensitive to the boundary conditions. And so then let me just very briefly say that we have this really nice works also in more condensed matter type scenarios, where we get this aperiodic spin chain, which reflects this construction principle of the bulk tiling. And so I don't have time to show this now, but let me say that we use some particular DMRG, strong disorder, so SDRG, sorry, techniques to evaluate the ground state of this spin train model. And so this can be implemented. So then we can calculate the entanglement entropy, and we can implement this in a tensor network. And so that already gives a different approach to. So the tensor network kind of represents again the gravity theory. So that's another approach. But here in this model, of course, there's no dynamics. I mean, tensor network looks like a hyperbolic space. And so we have the entanglement entropy on the both sides of the correspondence, and of course, the functional dependence on the entanglement region is the same with this log, but the prefactor, the central charge, is different because, in the duality maps weak to strong coupling, and at the moment everything we have is weak coupling on both sides. So that's something very interesting, and maybe somebody's interesting to look at these papers. So this is how to calculate entanglement entropy there. And then the last thing, which I don't have time to talk about, is these Majorana fermion chain. So this is again a condensed matter model for structures of von Neumann algebras that are investigated in ADS-CFT. And so again, maybe you're interested in looking at this. And so there we do have a particular phase transition in the model. So you see this is a chain with just four sides. There's a hopping between the sides, and there's a coupling at each of these sides. And there's a transition between, so the green lines are the correlations. So here in this case, the dominant correlations are between the first and the fourth and the second and the third. But if you go to another region of the phase diagram, the correlations are like this. And that looks like a transition between a wormhole and a situation where there's no wormhole. Okay, and this you can also map again to something in gravity, and so there's some topology also involved. There's a holonomy which you can associate to the wormhole. So there's a really nice similarity between something in condensed matter and in gravity. And the nice thing is that because it's finite, I mean, we have large n Majorana fermions, but since we only have four sides, we can calculate the type of von Neumann algebras and get a whole phase diagram of von Neumann. And so there's a really nice, so it's a kind of finite dimensional Hilbert space version of a wormhole. So that's a kind of very cute toy model. Okay, but I'm really sorry for keeping you for so long, but maybe you're interested to take a look at all these things. And let me just finish by saying that we follow this program of discrete holography towards a new example of a holographic duality, which is of relevance in quantum gravity and condensed matter physics, but also has some very interesting mathematical aspects. So the outlook is now to follow this avenue of this discretized JT-Yakif-Teitelbaum gravity and find the corresponding matrix model at the boundary. Conversely, if you start with the antiferromagnetic model, we are aiming for this gravity dual of it. And then we would like to implement strong coupling for these boundary spin trains, again, to find a dual. And I mean, there's also, we could think of making these bonds actually fluctuate, which would be a new approach to quantum gravity as well. So there are still many things to do in lots of directions. So thank you very much for your attention.